in the first dimension, a particle is isolated based on size, and in the second dimension, the identity of the organic coating is determined with mass spectrometry. There's of course time of flight, secondary ion mass spectrometry, a thermal gravimetric infrared gas chromatography mass spectrometry for organic particles, and this is a very nice technique which nowadays is also used to determine microplastics. Of course, there's again the transmission electron microscopy, this time with energy dispersive X-ray spectrometry to get more information about the coating of the materials, and the same you can do for scanning electron microscopy, which is more often equipped with this energy dispersive X-ray than TEM actually is. And the last one here is capillary electrophoresis with mass spectrometry. The last key descriptor for registration is specific surface area, which has to be determined. The surface area is measured as the total surface area of the substance, including both the internal and external surface of the substance. And the information can represent the total surface area based on mass unit, or it can be on volume unit. And as you can see here, this specific surface area is also being used to determine whether a material is a nanomaterial or not, which is the case if the volume specific area is larger than 60 square meters per cubic centimeter of a nanomaterial. There are two methods available to do this. The first one is the gas absorption using the Brunauer-Emmer-Teller isotherm. And well, we probably know when the principle of that is based on an adsorbat, typically an inert gas as nitrogen that is adsorbed to the surface of the material as a monolayer. And from the adsorption isotherm, you can then calculate the specific surface area. A little bit less known probably is nuclear magnetic resonance, which may also be applied here. What happens here is that it detects the differences of adsorbed and free hydrogen nuclear relaxation times after elicitation by magnetism. And the ratio of the two is then being used to calculate the specific surface area. This was the last key descriptor for registration. We had four key descriptors which have to be determined here, and we now have seen the methods which can be used to do that. So let's skip to the next important issue, which is risk assessment. Nanomaterials are widely used in many sectors of our society, and many new materials are produced every day, and that is quite a problem because we want to do some risk assessment, and you can't do that for all the materials. And so this risk assessment of nanomaterials faces difficulties as it requires extensive data sets on physiochemical parameters, hazard identification, and exposure assessment, and therefore some prioritization is needed. You have to decide which are the important ones to do first. Well, to do that, Bayesian networks have been proposed as a potential tool in risk assessment to identify those nanomaterials that should get priority in the risk assessment. The first step in the development of such a network is determining the relevant variables. Well, which are the key descriptors, of course, in the risk assessment of nanomaterials. Now, that is exactly what we want to know for our nanomethod decision tool, and so we can use the results which they have found here. And in a recent study, 2 rounds of expert consultation were used to determine which key descriptors are most relevant for risk assessment. And the results of the survey are shown in this slide. And so, according to international experts, and it is outside ACEnano, the important issues here are solubility, shape, particle reactivity, surface area, particle size, status of aggregation and agglomeration, surface coatings, and surface charge. And so now let's have a look again at these. How do we determine these key descriptors? Which methods are at our disposal? So first, let's look at this one. This is just a slide naming them again. I just mentioned all of them already, so we can skip this one. Go to solubility now. And as you can see, we have a number of methods here which can be used to determine solubility. In principle, each method capable of determining particle size can be used to determine the solubility if you measure at 2 different points in time. Methods which are possible are dynamic light scattering, nanoparticle tracking analysis, field flow fractionation, UV vis would also be possible, and also possible is ultracentrifuge or ultrafiltration combined with ICP-MS. And that's an alternative that you can use to remove or to isolate your particles by centrifugation or filtration, and then determine the solubilized material by ICP-MS, which of course only works if it is inorganic material. An interesting one here is single particle ICP-MS, since this is the only technique that can simultaneously determine particulate material and solubilized ionic material. And there has been a lot of research in the ACEnano project to determine solubility using single particle ICP-MS. So that's an interesting one for here also. Again, of course, our transmission electron microscopy and scanning electron microscopy, which can be used to determine particle size, and from that whether or not a particle has a certain solubility or not. The next one is shape, and this shape was of course already mentioned in the regulation. And so electron microscopy again is here the choice we could make for techniques that can be typically applied for the analysis of shape. And you really want to see your particles here. And so this is scanning transmission electron microscopy again, scanning electron microscopy, or atomic force microscopy. The next key descriptor for the risk assessment is particle reactivity, and that is a little bit more difficult one because there are not many methods to determine particle reactivity. Luckily, one method has been developed in the ACEnano project, which is a reactivity assay, which can be used to get an idea of the reactivity of the materials. In the assay, reactive materials catalyze the reduction of methylene blue, and this catalytic reactivity is measured as a change in the methylene blue absorbance. And so currently, this is the only method here which is selected for particle reactivity. We are still working and looking in the literature to find one or two different methods which may also apply and would give us some more room for other methods. Another one here for risk assessment was surface area, and this one we already saw again in registration. The methods to determine surface area are already mentioned in regulation, and only two methods are available. This is the BET method and the NMR method we mentioned before. Particle size then, that's a well-known one, and there are a lot of methods here which can be used. It's dynamic light scattering which can be used, nanoparticle tracking analysis, field flow fractionation, more specifically AF4, which is often being used, and you have to remember that AF4 is actually a size separation method. It does not really determine size, but combined with a detector, which may be a multi-angle light scattering detector or an ICP-MS, and you can determine particle size with AF4. UV vis is another one which can be used. Of course, here we have the electron microscopy methods, transmission electron microscopy and scanning electron microscopy, which can be used, and also atomic force microscopy. An interesting one is also single particle ICP-MS, since there is a lot of work done on this in the ACEnano project. The developments go into the direction of simultaneously measuring multiple elements and smaller particles. And multiple elements is with traditional ICP-MS is often not possible because you have to run your analysis at a very high time resolution. And so generally you can only measure one element, but using a time of flight mass spectrometer, you can measure more elements at the same time, which is very useful when you measure composites. It's also going for smaller particle sizes. The regular instruments now measure somewhere around 20 nanometer as the smallest particle, but I know that in the ACEnano project they are already down to about 5 nanometer as the smallest particle that can be measured. And the last method which is here is small angle X-ray spectroscopy, which may also be used to determine size. Another key descriptor was aggregation and agglomeration. Well, primary particles that are chemically bonded form an aggregate, as you know, and primary particles and aggregates that are physically bonded form agglomerates. And as a consequence, agglomerates may break up during the analysis into primary particles and aggregates, but these aggregates usually do not break up into primary particles. And so if you measure these aggregates, for instance, with single particle ICP-MS, then in general, your method will tell you you have a large particle instead that it are actually aggregates of small particles. And in generally, this means that only an imaging technique like electron microscopy can reveal whether a particle is a primary particle, an aggregate, or an agglomerate. So just as for size or for shape, sorry, we have here three methods which are available, which is transmission electron microscopy, scanning electron microscopy, and atomic force microscopy. Surface coating was another key descriptor which was of importance for risk assessment, and we have looked at this a little bit earlier already. Within the ACEnano project, again, a number of techniques are being developed or used or improved, and one based on liquid chromatography and mass spectrometry for the identification of organic nanomaterials, and one based on laser desorption ionization for the identification of organic surface coatings on inorganic particles. TOF-SIMS is also being used, and also are being used the TEM and SEM method, which are mentioned here. And so again, here for surface coatings, we have quite some methods which could be used to identify the coating on the particles, which is again laser desorption ionization, matrix-assisted laser desorption ionization. Again, two-dimensional liquid chromatography mass spectrometry, very interesting because you can also separate on size, so you can select your nanomaterials. Time of flight is being used, thermogravimetric infrared gas chromatography mass spectrometry. The two electron microscopy methods are being used, and the last one here is again capillary electrophoresis combined with mass spectrometry. Last one of the key descriptors for risk assessment is the surface charge, and the surface charge has been measured as a zeta potential for decades for colloidal suspensions, and which may consist of particles in the nanometer range. And the measurement technique is electrophoretic light scattering, which is often combined with dynamic light scattering. So if you have a DLS instrument, you can probably also determine the zeta potential with it. And so here we have two methods which could be used to determine surface charge. That's electrophoretic light scattering, and that is capillary electrophoresis combined with mass spectrometry. Our last group in which we are interested is labeling. And labeling is important because nanotechnology is an enabling technology which uses the novel properties of materials with nanoscale dimensions or structures. And this means that the use of nanotechnology presents manufacturers, retailers, and consumers with new opportunities, but also with potential risks. And however, the potential risks associated with the use of manufactured nanomaterials in consumer products are not well understood. And therefore, it is useful or appropriate that consumer product labeling is being done to identify ingredients in nanoparticle form in the products to inform consumers of their presence in final products. And that is being done already for cosmetics, but it's also for biocides and food. And probably you know there is a lot of things going on about titanium dioxides, for instance. Should that be in materials or not? And it is banned in certain countries like France, for instance, because there are doubts whether this is okay or not. Well, the European Commission has published a recommendation on the definition of a nanomaterial and to promote consistency in the interpretation of the term nanomaterial for legislative and policy purposes in the EU. And it uses size as the only defining property of the material. And so the key descriptor here will be size, and we can have a look. We've looked at these methods before. Particle size determination for product labeling are again these methods we are lining up here: dynamic light scattering, nanoparticle tracking analysis, field flow fractionation, UV-Vis. Also included here now is the BET method, even that it determines specific surface area, but this may be a guidance for the size of the particle. Of course, the electron microscopy methods are in the single particle ICP-MS and small angle X-ray spectrometry. Okay, we've done a lot already. We've looked at the several key descriptors that are important. There are about 10 of these key descriptors now we've finished, and we've looked at the methods which can be used for these key descriptors. Now let's have a look at one of the other things, at the nanomaterial properties, and whether these methods, which we mentioned in the key descriptors, are applicable will also depend on the nature of the material and the limitations of the method itself. For example, while over 10 methods are mentioned to determine particle size, only microscopy will be able to size a material consisting of particles smaller than 10 nanometer. So if we know that we are looking at small particles, we already know that electron microscopy would be a candidate. To make a useful selection, or knowledge of the material properties has to be matched with the performance criteria of the methods. And these material properties were already defined as a set of questions in the NanoDefiner e-tool, and these are used here also. So let's now have a brief look at the most important material properties we want to know. The first one is actually what the material looks like. Is it a solid, is it an aerosol, or is it dispersed in a liquid, so a suspension? And this is important since certain characterization methods are only suitable for nanoparticles dispersed in a liquid or a powder. For instance, the BET method works only for powdered materials, while DLS works only with suspensions. And therefore, the primary grouping is done by the physical state of the material. Is it solid, dispersed, or aerosol? The second nanomaterial property is the dispersibility of the material. Some characteristics will only work on dispersions, and the following dispersions or visibilities are being considered. It may be that the material is not dispersible at all, so in that case only BET and XRD, for instance, would be working. But it can be dispersible also in aqueous media or non-polar media or polar media, or perhaps even in a material-specific media. Everything we know about this is being used to select the best method to determine these particles. Another one which is obvious, of course, is the chemical composition. And this is one of the most important criteria, since the characterization method has to be chosen accordingly. For example, an ICP-MS can only serve as a detection technique if the material is inorganic and contains elements which are suitable for detection with ICP-MS, for instance, silver or titanium dioxide. And therefore, we have again made different groups. It may be inorganic materials, carbon-based, organic materials, perhaps even biological materials which you're looking for. It may be composites, so materials composed of two different materials, or it may be even something other, which I don't know what that could be, since many are already mentioned here. It's also beneficial if we know anything about particle shape, since some methods will not be able to detect certain particle shapes. A single particle ICP-MS, for instance, will express each particle size as an equivalent spherical radius. So if you are dealing with a material which is the form of rods, you may have a problem here. And the same way, electron microscopy will have difficulty scaling flat objects. So the shape of the nanomaterials can be classified as follows. It may be a sphere, it may be equiaxial, it may be elongated, it may be a flat particle, a stainless steel platelets we analyzed some time ago, which was quite difficult even using electron microscopy. Or it may be a mixture of different scaled nano objects. Particle size range is of course important. If we know anything about the material we want to test, whether it's large or small particles, then we should put this into the tool also. And transmission electron microscopy is mentioned here as one which can handle a very broad range, 1 to 1000 up to 10,000 nanometer, while small angle X-ray spectrometry can only do a limited range up to 100 nanometer. So the suitability of the method here, it will be very much limited by what it can handle in particle size range. So everything we know is good. Also important is the presence of sub or supersized particles. Next to the particles of interest, the material may contain other particles with the same or different chemical composition, with much smaller or much larger sizes. And depending on that, the method may have more or less problems with it. And for example, the results of dynamic light scattering, but also nano-tracking analysis, are strongly influenced by the presence of only a few supersized particles. As an example, we recently analyzed a sunscreen material that contained a high number of small titanium dioxide particles and a much smaller number of large zinc oxide particles. DLS and NTA both measure the larger size particles without noticing the larger number of small titanium dioxide particles. So the method we choose here will depend on whether or not such large particles are present. Yeah, the other one is aggregation and agglomeration. This is a little bit the same as these supersized particles. And depending on which method we choose, it may have problems with the presence of aggregates and agglomerates, and that will influence the particle size distribution. And so if we have any information about this, we should mention this when we are applying the tool. Then we have two last ones which are important for electron microscopy. That has to do with vacuum conditions. Some materials are sensitive to vacuum conditions, such as in electron microscopy. And in that case, we cannot use electron microscopy as a technique to analyze the materials. And the same is true for sensitivity to electron beams. If the material is sensitive to electron beams, and many organic and biological materials are, they cannot be reliably characterized with electron microscopy. So this is, of course, then also an important item to know when we are looking for the best method. Well, we've looked now also at some of the nanomaterial properties, which are the things we have to know when we use a tool. And the last one we have to look at here are the method performance criteria. And to make a useful method selection, or knowledge of the material under investigation has to be matched with the performance criteria of the methods. And these performance criteria have been discussed with experts in the ACEnano consortium for all the methods we apply, and have been listed in the form of tables for the applicability of applicable analytical methods that were mentioned before, and to determine these key descriptors. Well, in total, we have mentioned now about 20 different methods, and so we also have 20 different tables which give an impression of the performance of the methods in terms of sensitivity, trueness, robustness, and precision, but mainly about what the method can do, what it can handle. Can it handle powders, or can it only handle suspensions? As an example, I have a table here of transmission electron microscopy. This is what the information looked like. And so this is transmission electron microscopy, and as you can see, it can handle all the materials, so powder, suspension, and aerosol. It can also handle all kinds of suspensions, since the liquid is evaporated anyway, and it can handle all types of chemical compositions, although this is a little bit less for the organic and biological materials, which can be a problem since they may be sensitive to vacuum or electron radiation, but that will come on later in the sheet also. The sheet also shows it can handle most shapes, with the exception of materials that are flat, which are difficult to visualize with EM. This is the first part. This is the second part, where you can see, does the technique use vacuum conditions? Yes, it does. Does it use electron beams? Yes, it does. There's some information here about what kind of sample support is required, whether it can handle polydispersive materials and multimodal mixtures, and another number of other questions which are handled here for functionalism, light absorption, fluorescence, and aggregation and agglomeration, and whether these are problems for transmission electron microscopy or not. Also, just in the image, I guess, is what is the size range of the technique it can measure. This is 1 to 10,000 nanometers, so it has a very large size range that it can handle. The last part of the table is, well, a number of other characteristics which are presently not used in the e-tool, but may be added as extra information. We are still working on that to add additional information to the e-tool, which would then be available directly or through the knowledge data warehouse, which is also part of ACEnano project and can give you additional information. Helpful things like sample size, for instance, is in here, but also a judgment on sensitivity, trueness, and most importantly, perhaps the availability of the technique. If you decide that you want to use the technique, the question is, can you find it around each corner, or are there only a limited number of laboratories which have such equipment? And you can see it has the label low here, indicating that for transmission electron microscopy, the availability is limited. Okay, this all has been going into an Excel sheet. This is just an impression here of the first version of the method decision tool, which was made in Excel. Total, it has two worksheets, one for the input and one for the matrix. And what you are looking at here is the worksheet containing the method performance characteristics of the method itself. Well, in the end, of course, doing in Excel is not so very easy. So the Excel-based tool was converted into an online application, of which you can see a picture in this slide. It is essentially the same, doing the same as the Excel tool is doing, but it's far more user-friendly and easy to use. And we will have a look at that in more detail shortly. Well, where are we now? Presently, we are in the process of validating the e-tool. We do this by using imaginary nanomaterials for which we answer the questions and then see what the outcome is. And this is a list of a number of materials which are being used here. And so it's simple materials like gold nanoparticles, but also more complex ones like Coatsum C, which is an organic material, plastic materials, large and small materials, and also things like nanosteel platelets, which are difficult to observe. The outcome and necessary collections to the e-tool will come later, and like I said, this is still an ongoing part. That is my presentation. I already thank you for your attention so far, but we now move over to the e-tool itself. And therefore I have to go to a website, so you have to give me a little time to do that. Let's see. Yes, I am there. And now you can see it if it's okay. This is the start page of the Nano Method decision tool. Just some text tell you what it is. So the focus of the Nano Method decision tool, which is based on the Nano Definer e-tool, is the recommendation of a suitable measurement technique based on a material description by the user, so that is by you. And based on the interest of the user, 3 categories are now available, which is important for regulation, for risk assessment, and for labeling. And for each of these, a set of parameters needs to be determined and is shown in a second window. So let's have a look. We start here, and then you get this second window where you see these 3 groups: regulation, risk assessment, and labeling. And if we click further on regulation, you get these key descriptors I was talking about: size and size distribution, shape and aspect ratio, surface functionalization, and surface area. And if you then finally decide that key descriptor is, for instance, size and size distribution, which you want to determine, you can click on this one, and then you get here the questions, the material properties I was talking about, what it will ask you. And so we have a list of questions here. I have to move this a little bit further. Then you can see these questions are also listed here at the bottom. And each time you answer a question, the label here will turn green, showing you that you already did this. But you can also use this to maneuver through the questions very quickly. But you can also scroll to them in this way. On the right side, you see the methods. You remember probably that there were 5 methods which were suggested by the ECA Annex, which could be used to determine size and size distribution. They're all in a black color at the moment because we didn't do anything yet. And as you can see, there's also a small info label involved here, which you can use, which you can click on to get more information about the methods. For some, the methods, this method information is already in, but for many others not. We are still working on this. But I can show to you if you click on DLS, like here, you move over to the data warehouse, the knowledge data warehouse that is in ACEnano, and you see you get some information about dynamic light scattering, a description of how it works, what the endpoints are, but you see there are also measurement protocols involved already, which you could have a look at to see how it is done. And so if you do or use this tool and end up with dynamic light scattering and you're asking yourself how is this being done, you can find additional information here. And there is, for instance, the measurement protocol for the analysis of cold nanoparticles using DLS, which was used in an interlaboratory exercise. And there are also sample preparation protocols, and there are also some data sets involved, and people who have provided information for that already. And so this is what you have extra. Now let's have a look at how it works. So we just start by answering questions. The first one would be the question, what is the current state of the particle component? Could be a powder, for instance, like here, and now you see that all my methods turn into an orange color, which means that these methods may be possible, but that more information is needed to decide whether it is useful or not. I could also click on suspension if I think it's a suspension, and now you can see that one method, BET, turns red, indicating that this method is not applicable for a suspension, and that's indeed the case because we can use that only for powdered materials. Aerosol may also be possible, and you see that multiple methods are not suitable for aerosols, and DLS and SAX is also not suitable for these aerosol materials. So just let's leave it at powder, because we then have most things to choose from. Specific dispersibility in different media is then the second question. Is it dispersible? Suppose it's not, then DLS falls out because DLS will only work for suspensions. And so I can't use DLS in this case. But if it's dispersible in aqueous media, it will do DLS, of course, and it will still be possible. Dispersible in non-polar media, DLS also turns red, and I know that people have done DLS using hexane as a solvent, but it's not very usual. And so in general here we say it's not possible for non-polar media, but it is possible for polar media. And it is, again, not possible for material-specific media, which may be anything special, but generally it requires additional chemicals to be added, which may interfere with the DLS determination. So let's leave it here. What chemical composition do you expect? So what may it be? Suppose it's titanium dioxide. So we would say, okay, it's inorganic. Well, we can use all methods still possible. Nothing is excluded. Same for carbon-based, organic. Biological, PET goes out because that won't work for biological materials. Composite is possible. And if we choose other, you can see DLS is also out of the question. Let's leave it here at inorganic. Do you expect composites? Well, I should have mentioned that here, of course, but it may be no composite, no problem, but in this case, composites are still possible for all methods we have here. What shape do you expect the particles to have? That's an interesting one, and normally if it's a sphere or similar, then all methods have no problems with that. It's equiaxial. Still no problems. These are cubes, for instance, or prisms, a little bit like a sphere. All methods are possible. Tubes is a problem for DLS because DLS will give you an average size and not any specific for a tube-like material. And if you have flakes, SEM and TEM, like I mentioned before, are also problematic because they have difficulty observing that. Other, you can see one more goes out, and mixture will be the same. We leave it here at sphere. How many small dimensions do you expect the particles to have? Well, they may have one. This is in case you know how many small dimensions you want to determine, and you have difficulty answering question 5. These are the tubes. These are the flat materials. These are the tubes again, of course. DLS is a problem, and this is spherical materials where there is no problem. The important one is, of course, size range. What do the methods allow us to determine? Well, let's say that the minimum size range is 10, and maximum would be 200. And then you can see SUX falls out because the maximum SUX for SUX is about 100 nanometer, so it can't work up to 200 nanometer. But there's also a limit on the minimum size. If I just lower this to 9, you can see that DLS and SEM also are no longer included as suitable test methods because they don't go beyond 10 nanometer. At least that is what we think is reasonable for these two methods. So we're just going to leave this one at 10, this one at 100. To extract these particle sizes, I already explained when we talked about these larger particles which may be present, and that may be a problem for DLS, and that's also what we see here. It's a problem for DLS, but it may also be a problem for SUX because that runs quite easily out of the range it can handle. Significant aggregation may be a problem, and it's a problem for two methods, for DLS and PET, which may then not be used. So I'm going to move to this one because I'm running a little bit out of time. And now the interesting thing is that you can see that two methods are becoming green. So tool now says, well, SEM and TEM are two methods which you probably can use for this material. So let's just move on. Agglomeration, DLS is still a problem, so it won't work. It's turning red. And now you see it's not the case, and all the other methods also turn green. And so at the moment it's safe for the material you are answering the questions now for. All these methods may still work. Multimodality, just having two peaks in the size distribution, if that is close together, that's no problem. Moderate is also no problem, but if the peak size is different, again, DLS and SEX run into difficulty in determining the peak size, and so they are turning red. Polydispersity may also be a problem, and not here, but highly dispersible materials are problematic in SUX determination, and so therefore that one is turning red again. Two important questions I mentioned was instability under vacuum conditions and electron radiation, and you can see that happening if you say yes. If it's unstable under vacuum conditions, and then PET, SEM, and TEM, all three using vacuum conditions, turn red, and they cannot be used for the determination of this material. Same is true here for electron radiation. That's only SEM and TEM, which then turn red and can't be used. Okay, we have 4 more questions to go. Electroconductivity in this case will be no problem for these materials. Same as for light absorptive properties, which is no problem also. Functionalism, which may help to suspend a particle, so it's adding if it's yes, but it's no problem here. And do you expect ions, atoms, or molecules to be released? Well, yes, in that case, DLS and PET turn red because in that case you may run into problems with that material. So we now just went through it just to have a look how it works. Let's now try to do, I hope I can still do 2 examples with you for specific materials. So let's just do that. Let's go to risk assessment, and then let's look at a coating, for instance. Surface coating, and we are looking here at a liposome material that we had some time ago, which is a powdered material which can be used to coat particles and to make them more suspendable, or it can be used to coat active ingredients also. What do I know of the material? Well, I know it's a powder, so I know that. I also know it is dispersible in aqueous media. Until now, all methods are still possible. What chemical composition do I expect? Well, I expect it to be organic, and now already you can see that a number of them turn red because they are not suitable for these organic materials, which is LDI, TOF-MS, but also the SEM EDX and TEM EDX turn red because EDX will not give us much more information than only that it is carbon, and we know that already since we know it's an organic material. Do we expect composites? No, we don't. Do I know anything about shape? Well, it will be more or less spherical. The material forms kind of micelle material, so spherical. How many dimensions do I expect? Well, it's 3 in this case. I know from the manufacturer what the size of the materials are. I know that the size is somewhere between 50 and 200 nanometer. And as you can see, for all these methods, there is no problem with the case. Do I expect larger or smaller particles? No, I do not for this material. Do I expect significant aggregation? Answer here is also no. And now you can see that a number of methods turn to green, and they say, well, we are probably able to identify this surface coating. Do you expect agglomeration? Answer is no. One more turns green. And which grade of multimodality do you expect? Peak size differs small. It is quasi-monodisperse. Do I expect instability under vacuum conditions? Well, yes, that could well be because it is an organic material. And so top sims now is also out of the question. Do I expect instability under electron radiation? Yes, again. And so we get some more red here. And do you expect particles to be electrical conductive? No, it's organic. I think it's an insulator. Light absorptive properties, not that I'm aware of. So I say no, or could be that unknown if I don't know. Do you expect functionalism? Well, yes, actually I do from these materials. And the last one, do you expect release of ions? And the answer is no. And then what you can see, we have a number of methods here which are red, which cannot be used to identify this material, but also a number of which are green, which could be used to identify this material. And actually, we did analyze the material in ACEnano, and two methods have been used to do that. And that was the 2D LCMS, which allowed us to characterize the material as indeed a nanomaterial, but also to correctly identify the surface coating of the material. And another way which was being used, which was an offline analysis, was MALDI-TOF-MS to get information about particle composition of these materials. And so from this, we get a useful selection of methods which may be used to identify these materials. We just have time to do one more, so let's go one for labeling. And then I think we do a cosmetic sample because very recently we had a sunscreen material which was being analyzed in the interlaboratory exercise. Which is, I think, an interesting one because it was a very complicated sample and we got a lot of questions about it. So let's just do again that we don't know anything apart from having the bottle of sunscreen material on our table and the listing of the ingredient list. And from that, I know, of course, that what this material is a suspension. And you can see two methods which were mainly for powder materials, XRD and BET, turning already red. They cannot be used for this material. It's a suspension and we dilute it in water to get it in a concentration range which is suitable for the analysis. So it's also dispersible in aqueous media. We saw that. What chemical composition do I expect? Well, I know that from the ingredient list. It tells me that it contains small sized titanium dioxide particles with the label nanomaterial. And so this must be really small. But it also contains zinc oxide with no label. So these are probably larger zinc oxide particles which may be in there. Anyway, what I'm looking for is inorganic. And still all methods are orange. Do I expect composites? Well, the answer is no, I do not expect composites. What do you expect from particle shape? Well, actually, I don't know. We didn't on beforehand look at it already with the electron microscopy, so we have no idea, but I expect these to be spherical or equiaxial, so I just select this ones. And I have no reason to assume that it are tubes or certainly not flakes which are in there. So how many small dimensions do I expect? Well, I expect just 3 small dimensions. Particle size is, of course, an interesting one because I expect these titanium dioxide particles to be rather small. And so I select 10 for the small size, and the zinc oxide will be much larger. So I just choose 250 for zinc materials. And now you can see a number of other methods turned red also. And the first one is NTA, for the simple reason that it cannot observe these small 10 nanometer particles. If I change this one into 20, it may be just not okay. Okay, select 30. And if it's 30, then NTA would still be in, and also with single particle ICP-MS. But I expect they may be smaller, so just leave it at 10. So NTA goes out because it can't see these small particles. Single particle ICP-MS also is out because it cannot see these small titanium dioxide particles. I think the limit there is about 20 or 30 nanometer for usual ICP-MSs. And I know the one developed in ACEnano will probably be able to measure somewhat lower, or you need a higher resolution ICP-MS, and that can maybe just reach this limit of 10. Next question is the presence of sub or super nano-sized particles. Do I expect them? Well, actually I do, because I know that there is large zinc dioxide particles in there. And there was no mentioning of them being nano, so they probably are bigger. And now you can see that the method for DLS also turns red, because it will have difficulty sizing these materials. Do you expect significant aggregation? Well, yes, that may be. And for the titanium dioxide, it's a very sticky compound, and there may be some aggregation there. And so now I see that AF4, because it cannot discriminate between primary particles and aggregates, also turns red as being no longer useful to do this. Do I expect agglomeration? Same reason, yes, may also be some becoming a little bit redder now than they already were. Do I expect multimodality? Well, not for the particles themselves. They will be, I think, about same size. Polydispersity, let's say, moderate. You can see UV vis now also falls out because it cannot do that. Do you expect instability under vacuum conditions? Well, the answer is no, I don't expect that. And electron radiation also for titanium and zinc oxide will be no problem. So no. Electric reconduct, I honestly don't know for titanium dioxide and zinc oxide. They may be semiconductive, so I answer that. Light absorptive properties, well, yes, of course, that's the reason why they're in. Do you expect functionalism? No. And do you expect? Answer is no also. And as you can see now, most methods turned out red, and they are for one or more reasons not useful for this analysis, and only 3 are left, SEM, TEM, and AFM, which may be used to analyze these materials. And that's actually what we did. In this case, we used TEM to analyze the materials and found out that they were small titanium dioxide particles with sizes around 10 nanometer, and larger sizes, zinc oxide particles, which had sizes around 150 nanometer. Not knowing this on forehand, we also use different methods. We also use single particle ICP-MS and found out that we did find particle sizes in the range of 30 to 50 nanometer, which is not the actual size, but which is probably the size of the aggregates which are in there and which were found by the single particle ICP-MS. We also did NTA and DLS, and then we had even more difficulty. And the sizes we found there were over 200 nanometer, indicating that NTA and DLS just focus on the larger zinc oxide particles and don't see the smaller titanium dioxide particles. And so the, let's say, suggestion by the tool to use TEM was a good one, and he was right that the other methods would not be able to size these materials. And that is, I think, what I wanted to show you. Thank you very much for your attention, and I'll go back to the chat, I think.
Thank you very much, Professor Peters. Now the paper